Fisher projection formula always represent molecule in eclipsed conformation. It's very important statement that I am going to give. See, if you will take any molecule, this is which projection formula? Fisher projection formula. And if I draw its Newman, so this is carbon number 3, CH3, OH, H, and behind that there is a presence of carbon number 2, OH and EH. This is which projection formula? This is Newman projection formula. And dihedral angle is equals to 0. That's why this conformation is eclipse conformation. What statement I have given? Fisher projection formula always represent molecule in eclipse conformation. Now if I have written or if I have taken the molecule in the staggered form, if I have written the molecule in the staggered form, why this is known as staggered form? Because dihedral angle of this is equals to 180 degree. Can I write directly staggered to Fisher? No. Fisher, this staggered conformation I have to convert to eclipse and then eclipse to Fisher. So this is the most important statement everybody should keep in mind. So my dear student, what we have done, we have started with what we have done. Just we have a summary. Look first. We have started with isomers. Isomers are the compound having same molecular formula, different structural formula. Then it is structural isomer and stereoisomer. Structural and stereo just we have done. Structural isomer further divided into 5 types. Which are they? Chain, then functional group, then position, then metamer and tautomer. This is the most interesting concept we have done. And in the stereoisomer, before starting stereoisomer, what we have done? We have done projection formulae. Which projection formulae we have done? Fisher, then Sohars, then Newman we have done. After that we have done dihedral angle 0. It is known as eclipsed conformation, and dihedral angle is equals to 180. It is staggered conformation. So conformation is the phenomenon of isomerism, rotation around carbon-carbon single bond. In the stereoisomer we have done conformational. It is classified as conformational isomer and configurational isomer. In the conformational isomer, when we have free rotation, it is eclipsed and staggered, and when we have restricted rotation. Now my question is, when we are having restricted rotation in carbon-carbon single bond. So tell me, when we are having restrictions, now for restrictions, so now I want to tell you one interesting thing. So it is carbon-carbon single bond. Now it is free to rotate. Now when there is a restriction, please see, if this carbon-carbon single bond, it is not becoming, if it is converting into a cyclic compound, Please see. When there is a presence of a ring or cycle, yes, so we cannot have carbon-carbon free rotation. So where is the free restricted rotation? Restricted rotation present in the ring, and for that we are getting different conformation. So I will tell in short, in the restricted rotation we are having chair and boat conformation because we are having restricted rotation. So that we will discuss in the next different article. So first of all, this is the phenomenon of isomerism, conformational, configurational. In the conformation free, eclipsed and staggered, and restricted rotation will be in the cycloalkanes. So these cycloalkanes we are going to discuss afterwards. Now when we are having this concept, we are going to discuss about configuration. See, listen, eclipsed, conformation, staggered, conformation, gauge, conformation, skew, conformation, R, configuration, S, configuration, small d, configuration. So now we are going to have a configurational isomer. Very interesting concept, that structure is same but what thing is changing. So now we are going to start with the configurational isomer. There should not be any confusion. Isomer, structural, stereo. Structural we are divided into these things. In that we have done projection formulas, then staggered and eclipsed conformation, free rotation. In the free we are having eclipsed and staggered, and when we are having restricted it should be cycloalkanes. And now we are going to start with configurational isomer. Now very interesting concept, what is mean by configurational isomer? So what is mean by configurational isomer? Configurational isomer further divided into two types. Number one, optical isomer, and second one, geometrical isomer. Configurational isomer further divided into optical and geometrical isomer. For understanding optical isomer, one should understand optical activity. What is meant by optical activity, or what is meant by optically active compound? Now it's very interesting and a very nice concept that our plane polarized light, our normal light propagates in all direction, but when that light will pass through a Nicol prism, that light will propagates in a single direction or single plane, and it is known as PPL, plane polarized light. And this plane polarized light use an instrument known as polarimeter, and this polarimeter is useful for finding the optically active or optically inactive compound. Now what we are going to do, what is going to happen, this is, I am drawing very rough diagram. This is a cuvette, this is the polarimeter, consider it is a knot, and this is like this. This is the source of a plane polarized light, and there is a presence of a needle. Your compound is going to fill in this, and you are going to find out optical activity. What is going to happen when we will start the source? Needle knows only two deflection, either in the clockwise or anti-clockwise. If needle shows clockwise deflection or anti-clockwise deflection, it indicates your compound is optically active. And if needle is not showing any deflection, your compound is optically inactive. What is going to happen? What is going to happen? This is the plane of the polarized light. This is your compound. The line which is I have written, that is blue, it is considered compound. What is going to happen when light will fall on the compound, and if compound rotates the plane of the polarized light, if compound rotates plane of the polarized light in the clockwise direction, needle shows clockwise deflection. And if compound rotates the plane of the polarized light in the anti-clockwise direction, needle shows anti-clockwise deflection. Have you understood? If compound rotates plane of the polarized light in the clockwise direction, needle shows clockwise deflection. If compound rotates plane of the light, so this blue is compound. This is also compound. When compound rotates the plane of the polarized light in the clockwise direction, needle shows clockwise deflection. Compound rotates the plane of the polarized light in the anti-clockwise deflection, needle shows anti-clockwise deflection. In both the cases, compound is optically active. When compound rotates the plane of the polarized light in the clockwise direction, it is known as dextrorotatory compound. It is shown by letter small d or plus sign. This is known as dextrorotatory compound. Rotation is known as dextrorotation. If compound rotates the plane of the polarized light in the anti-clockwise direction, it is written as small l or minus. It is known as levorotation. It is dextro and this is levo. Dextrorotatory compound and levorotatory compound, they are optically active. So compound rotates the plane of the polarized light in the clockwise direction or anti-clockwise direction. If needle is not showing any deflection, it is optically inactive. Now, if you are having 50% dextro and 50% levo, so this is equimolar mixture. So what is going to happen? Rotation gets cancelled, needle is not showing any deflection. Such a type of mixture is known as a racemic mixture. And racemic mixture is optically inactive. Racemic mixture is optically inactive. Now, one most important thing, it is known or it has been told, a racemic mixture is an external compensation. What is meant by external compensation? We are going to mix two different components externally. So it is external compensation. So racemic mixture is external compensation. So most important, this is dextrorotatory and levorotatory compound. Please see, for us understanding the concept of optical activity, we have started with our normal light propagates in all direction. When it will pass through Nicol prism, it will propagate in all direction. It is known as plane polarized light. This plane polarized light uses an instrument known as polarimeter. This polarimeter is having one needle. Needle is having two deflection, clockwise or anti-clockwise. It is showing optical activity. Why optically? This compound rotates plane of the polarized light in the clockwise direction. Needle shows clockwise. It is known as dextrorotatory. And if it will show anti-clockwise, it is levorotatory. This is racemic mixture is also shown like this. So equimolar mixture means it is also known as DL pair. It is optically inactive. Now this thing is correct, that optical activity is there. Compound is optically active. It is showing, everything is correct. But the most important thing is that the question comes, what is the cause of optical activity? Optical activity is there. See, we have started with optical isomer. Before starting optical isomer, we have done optical isomerism, optical activity. And in the optical activity, we have done that the concept of dextro and levo-rotation. The thing is that what is the cause? Cause of optical activity. And the cause of optical activity is chiral carbon atom. chiral carbon atom, it is known as asymmetric carbon atom, or it is also known as stereogenic center. These three things are one and the same. Now the question is that if in a compound there is a presence of chiral carbon atom, that compound is optically active. That is true. So the next question is, what is meant by chiral carbon atom? Chiral carbon atom, all of you know, sp3 carbon is a tetrahedral, and what is meant by valency? The different groups are attached. Now if valency of carbon is satisfied by 4 different groups, then this compound or this carbon is known as chiral carbon atom. Valency of carbon is satisfied by 4 different groups. This is the most important condition. Now you may ask me the question, sir, what will happen if the 2 groups are same and these groups are different? We cannot call it as chiral carbon atom. I have written little bit like this, because we have done in our previous lecture. See, if the 2 groups are same, what is going to happen? Please see. Now, this is chiral carbon atom. Agree? Because the 4 groups attached are different. Now what I will do? I will convert, or I will remove 1 group and I will put 2 groups are similar. See what is going to happen. You know that there is a presence of how many planes? 2 vertical planes. See, one is like this and one is like this. If 2 groups are same, what is going to happen? The molecule can cut into 2 equal halves. And when molecule can cut into 2 equal halves, the molecule is becoming symmetric. And if it contains element of symmetry, such a molecule cannot become optically active. Very interesting. If we will consider like this, the plane will be like this. If you will consider like this, the plane will be like this. Yes or no? So there should not be a plane of symmetry. Element of symmetry should not be there. So plane of symmetry, axis of symmetry. Now after this, I think you understood what is meant by chiral carbon atom. Now we are going to have a most important discussion on chirality of the compound. Now we have came up to optical activity. Now we have came at a thing that compound is showing optical activity. That compound must contain chiral carbon atom. Now we have to come at such a point that compound should be show optical isomerism. And for showing isomerism, how many things should be there? At least 2. So in the, I have told you initially, stereoisomer compound having same structure. What is changing? Only 3-dimensional arrangement is changing. In the conformational isomer, we were having 2 carbon atoms. But in the optical isomer, we are having only 1 carbon atom. So now how that arrangement is changing? So that is the interesting thing we are going to see. Now I will write down very simple compound, very interesting and very simple compound. The name of this compound is glyceraldehyde. Now the central carbon containing 4 different groups. Agree? That's why this compound is containing asymmetric carbon. And we know that the compound which contains asymmetric carbon, it is optically active. As this is optically active, it will show the phenomenon of optical isomerism. And you know that for isomerism, at least 2 things should be there. The most important rule is there, number of optical isomer is equals to (2 raised to n). where n is equals to number of chiral carbon atom. Now in this compound, how many chiral carbon atoms are there? 1. So 2 raised to 1 is equals to 2. So this compound shows 2 optical isomers. What is optical isomer? The compound must contain chiral carbon atom. That's it. Now how to find out the second optical isomer? We have to draw its mirror image. When we are going to draw its mirror image, OH, H, CHO and CH2OH. Yes. What is the relation between these two? Both the compounds are having same molecular formula. Yes or no? Yes. So they cannot become structural isomer. What is changing? Their three-dimensional arrangement is changing. In one case OH is on the right hand side, in one case OH is on the left hand side. So their three-dimensional arrangement is changing, means their stereochemistry is changing. Here we cannot have these two isomer interconvertible by rotation around carbon-carbon single bond. So we cannot call them as a conformational isomer. As it contains a symmetric carbon atom, definitely it is optical isomer. Now we have drawn the second optical isomer by its mirror image. Now we are going to discuss, or we have to first of all discuss the relationship between these two. Now what I will do, consider, you know that these two groups are facing towards you. This is going away, this is going away. Consider if I will hold this compound and if I will try to put it on this. What is going to happen? What is going to happen? Now here we are going to have a concept of superimposable and non-superimposable. Please see, my right hand is exact mirror image of my left hand. If I will try to superimpose this on this, please see what is going to happen. My 3 fingers will superimpose, but these 2 fingers will not superimpose. So are they mirror images of each other? Mirror image and non-superimposable mirror image. So what is going to happen? If I try to put this compound on this, they are mirror image, but they are non-superimposable mirror image. First of all, what are they? They are optical isomer. Agree? Optical isomer. First of all, they are optical isomer. Yes or no? Yes. These are optical isomer. Optical isomer which are superimposable or non-superimposable? Non-superimposable mirror image. Of each other, they are known as enantiomer. Yes, very much careful. So first of all, have you understood optical activity, optical isomer? And now we are entering into one interesting concept, what is meant by enantiomer. So first of all, enantiomer should be isomer. After that, it should be stereoisomer. After that, it should be optical isomer. And after that, it should be non-superimposable mirror images. So we'll go from enantiomer, non-superimposable mirror image, yes. Chiral carbon atom, yes. Same structure. So this is known as enantiomer. So what is the definition of enantiomer? Most important word should come, optical isomer, which are non-superimposable mirror images of each other. They are known as enantiomers. Now, enantiomers, as they are having same structure, they are having same melting point, they have same refractive index, they have same density, they have same physical properties, except what? Optical rotation. If we will put this compound in the polarimeter, if it is showing clockwise deflection, means polarimeter shows clockwise deflection, definitely if we will put B, it is showing anti-clockwise deflection. So enantiomers are having opposite optical rotation. This is the most important concept. So now we have came across a most interesting thing, non-superimposable mirror image optical isomer, they are known as enantiomers, and enantiomers are having opposite optical rotation. That we have done. Now, if there is a presence of one chiral carbon atom, if there is a presence of one chiral carbon atom, it will show 2 raised to n means 2 optical isomer. Now we are going to start with the compound containing 2 chiral carbon atom. It's very interesting, compound containing 2 chiral carbon atom.